Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Students, let us solve the next question, number 32 of NEET Physics 2014. Students, let us solve the next question, number 32. A thin semicircular conducting ring PQR of radius r. This is the radius r and this is semicircular ring PQR. Is falling with its plane vertical in a horizontal magnetic field. That means if this is the horizontal magnetic field is in this direction, then the semicircular ring is following its plane vertical. Falling vertical to its with its plane vertical. So plane is vertical. So if I take this is the ring, then this is the plane. So if this plane is vertical, it's like that. So it is falling like this. When it falls like this, it will cut the magnetic field. So a semicircular ring with its plane, this is the plane which is vertical, while falling will cut the horizontal magnetic field. As shown in figure, the potential difference developed across the ring between these 2 points when its speed is v is. So when I let the ring go down, fall down, it will continue to gain its speed, and it says that when its speed is v, by the time when the ring falls with the velocity b, at that time what is the potential difference created? That means the potential difference across the ends of the conductor depends upon the velocity of the conductor, because we know that if there is a conductor of length L carrying current, suppose I, is moved in a magnetic field, or if there is a I have to develop the potential difference, so I don't need current. I'll just take a wire, and if it cuts the magnetic field present, suppose this is moving, the magnetic field is into, suppose, then this is also subjected to downward magnetic field. Then, and it has to move with a certain velocity, suppose the velocity is v, then the potential difference that is created at the ends of these 2 points, potential difference, suppose this point is a and this point is b, the potential difference VAB or EAB, right? Rather I write induced EMF EAB equals to BLV. This formula we have already known. So this is the direction of the motion of the conductor. So therefore if I move the conductor in this direction, the force acting on the charged particles present, particularly electrons. If I think of protons, so obviously not moving, but if I think of the electron which is present there, if the conductor moves, the electron is also moving in that direction. We know that the force acting on a charged particle projected into a magnetic field, suppose that the magnetic field is in this direction, or might be in this direction, suppose. So QV is in this direction and B is downward, so the force will act in this direction for positive charge. Because it is I consider that this is the electron, so force will not act in this direction, force will act in this direction. So electron will start moving toward B side, and here it will be negative end, and here finally it will be positive end. Now, so there will be a situation when these electrons will be, so this end will be negatively charged and this will be at a higher potential, this will be at lower potential, and in this situation this conductor behaves like a battery and having its positive and negative terminal. And if I allow any closed path to form, then the current will start flowing in this direction and obviously from lower to higher in the conductor. Okay, but this is theory and you have to, so that means that EMF that is induced is given by this formula BLV, where L is the length and V is the speed. Now, if in place of this straight conductor, if I have a conductor like this, PQR conductor, and the magnetic field is into, then I have to think of this formula is directly used when the V is perpendicular to the length. But here V is not perpendicular to the length because sometimes the length is this, but the speed is downward. So all the velocity is downward, but the length is not perpendicular to velocity. So I have to consider each part of it and then take the component. So doing so, I'll just if I want to find the actual length or effective length of this ring between these 2 points, then I have to have a projection of this length on this line, and this is the effective length. So, so this is the effective length, and that equals to obviously the diameter of the ring. So the length, effective length, that is L over here, that will replaced by effective length. It is 2 of radius r. If r is the radius of this wire, that is the diameter, this is the effective length. So in place of L, I will substitute 2r. Okay, and if I substitute that, then the E potential difference across AB or PQ, obviously here PQ, it will be B, L is 2r and 2V, so that is 2RBV, 2RBV. So the potential difference across the ring, the speed V is what? It will be this one, that is this one, 2RBV, and R is that higher potential. You can see that if I rotate this and moving down, then R is at higher potential, obviously, because if this is moving down, then QV is in this direction and B is downward. So QV cross B, QV is in this direction and B is downward. So QV, if I QV cross B in this direction, in this case, as I told you, QV, B down. So in this direction, the positive charge will move, or in this direction, that is the higher potential. That means the direction of QV cross B will give you the direction of higher potential end. And the direction of QV means the direction of current. Now, this is moving in this direction, and this is downward. So QV, this is actually moving in this direction, and QV cross B is in that direction. QV cross B is down. So in this direction, there will be higher potential. And in this direction, the point is R. This is the point, R is in this direction. So R will be at higher potential. So the higher potential is determined by QV cross B. So this is the answer to this question. Okay, thank you.